Hello everyone, welcome to this presentation. Today we are going to continue with this topic related to BLDC motors. And in this presentation we will be talking about BLDC motors regulation. So we will see first an introduction, then we will present the general block diagram with the dynamic behavior of the system. We will show then how to design the compensator, and finally we will be performing several LTspice simulations to check that everything is working properly. For this we will be using the model that we developed in previous videos, LTspice number 15. We have developed here the BLDC motor model. In LTspice number 16 we also tested this model with a power converter. Then we showed in video number 17 how to do the control of the motor using PWM control. And in video LTspice number 18 we have shown how to obtain the dynamic model of the BLDC motor. So we are going to use this model today to understand how to do the closed loop operation of the BLDC motor. In previous videos we have seen how to drive the BLDC motor using our power converter and using this control circuit based on a decoder from the signals that are generated from the host sensors. Then we can finally generate the gate signals for the switches. So also we have seen in other videos that we can implement a PWM control in this way by adding the elements in blue here. So using a sawtooth waveform and a comparator, then we can modulate the signals of the three top switches, 1, 3 and 5. So then we can control from this control signal here, from DC voltage signal, we can control the speed of the motor. At the end, what we are doing with this modulation is the equivalent situation to change the voltage, the equivalent voltage VDC that we are applying to the motor. So what we are going to see today is how to implement the speed regulation of the motor by adding a regulator. So what we are doing is adding these elements here in red. We have a tacho generator in order to generate a DC signal Vs, which is going to be proportional to the angular speed. And then using this error amplifier, we are going to compare the speed with a reference value so that the compensator is going to generate the signal MVC with the required value in order to keep the angular speed of the motor constant. Here we can see in red the block diagram of the dynamic behavior of our system. Here we have the angular speed that we want to regulate. So we are measuring the angular speed with our tacho generator and generating this signal Vs. We compare this signal with our reference and then we generate the error signal that we feed into the compensator C. The compensator is going to generate the output signal VC that is going into our PWM circuit. And this is the gain of the PWM circuit that we are going to see right now. And then here we have the behavior of our plant, of the motor, that we have also obtained in previous video. So starting by this transfer function GC, we have obtained this equation, this expression for the transfer function of our motor. And then with our PWM modulator, we are comparing the control signal, the output of the compensator, with the sawtooth waveform. and then we are generating the PWM signal for the switches. The voltage VD that we are going to apply to our system is equal to the duty cycle times the DC input voltage. There is a mistake here, this is VDC. And also because of the behavior of the comparator, we also know that the changes in the duty cycle are 1 over VPP times the control signal BCS. So from these two equations, we can obtain the behavior of the complete PWM system. In our case, we are going to use a value of VPP equal to 1 volt, and also we are going to consider that the sensor of the speed, the tacho generator, is going to be just a gain Ks in volts per RPM, and in our case we are going to suppose that we have this gain 10 to the minus 3 volts over RPM. Now we have the model of our motor. We are going to use the same model that we have been using in these last videos. In the last video, we obtained these parameters for our motor, and then the transfer function GC has a DC gain of 33.8 dBs and a cutoff frequency of 638 Hz. We are going to implement a PI compensator with this response in blue, which is very well known. Here is the expression of the PI compensator, so it's characterized by this parameter here, Kc, and also by the frequency of the zero. So we have this response for the compensator, and then in order to do the design of the compensator, we need to obtain the total loop gain of our system. So in order to simplify, we are going to join these two blocks together in this transfer function GT, and then here in red we are representing the product of GT times our sensor H. So we have this response also very similar because this is a constant and also H is a constant. And then the total loop gain of our system is the product of all the blocks, and it is shown here in green, is GT times H times the gain of the compensator C. So the design is very easy. We only have to place the zero of the compensator at the same frequency of our system here. So the total loop gain is going to follow this line here. We have a minus 20 dBs per decade in this area here until this point here, at which we are going to have a slope of minus 40 dBs per decade. So in order for our system to be stable in closed loop, we know that the 0 dBs line has to cross the total loop gain in this part here corresponding to the minus 20 dBs per decade area. So something like this would be stable, and the limit would be that we get 0 dBs at this point here, at which we will have a phase margin of minus 45 degrees, which usually is good enough for regular applications. In this way, we can increase the bandwidth and the dynamic response of our system. If we cross the 0 dBs line at this point, then we will have this cutoff frequency F1 with a given bandwidth. But if we play with the gain Kc of our compensator, then we can move this line of the total loop gain up or down, and then we can cross the 0 dBs at this point and increase the bandwidth of our system. So this is the procedure, but in order to do all the calculations, it is better to use a mathematical software. We are going to use Python, and we will see how to do this in the next slide. So this is the script for designing the compensator using WinPython. Here we can see the different parameters of our motor. Also here the DC input voltage and the peak-to-peak value of the sawtooth waveform, the gain of our sensor. Then we have the transfer function GC, the transfer function, total transfer function GT, and then the compensator parameters. The zero frequency is going to be 638 hertz, so in radians is 2 pi this value. And then we have this value Kc that we have adjusted in order to make our system stable and with the desired bandwidth. So here is the expression of the compensator, and this is the total loop gain. And then with these statements here, we are representing the transfer function GT, the transfer function of the compensator, and the total loop gain. So here we can see in this graphic, here we can see in blue the transfer function GT. In orange, we can see our compensator. So in this area here is the zero of our compensator. And in green, we can see the total loop gain. So what we have done here is to try different values of Kc. So then we can move the compensator up and down until the green line, the total loop gain, crosses 0 dBs at this point here between the minus 20 dBs per decade slope and the minus 40 dBs per decade slope. So with this we can see that the phase margin is going to be 45 degrees and the bandwidth of our system is going to be around 600 Hz. Finally, this is the implementation of our compensator. Here we have the expressions with the values here that we need in our compensator. So we are going to do the implementation as shown here using an operational amplifier. And then we have these values for the angular frequency of the zero and the parameter Kc. So what we do is to choose a value of our capacitor C2, 10 nanofarads, for example, which is a very common value, and then we obtain these values for the two resistances of our compensator. So now we are ready to check our design by simulation using LTspice. Here we have the complete circuit that we have seen in previous videos, so I'm not going to enter into detail. What we are adding here is our sensor to measure the angular speed with this gain, as we have seen, 10 to the minus third exponent. And then we are sending this information into our PI compensator. So here we are using a reference value of 1.7. So this means that we want 1700 RPMs in our motor. Then here we have the compensator and we are adding here a limiter in order to limit the output of the compensator, because the sawtooth waveform that we are using here has a maximum amplitude of 1 volt. We are limiting here the output of the compensator between 0 and 0.95 volts. So we are assuming that we are always applying here a value that is between the sawtooth waveform. And then with, as we have seen with the PWM modulator, we are sending the signal to the top switches. So this is all in principle, so we can run the simulation and see the results. So we can take a look at the angular speed. So we see that we are getting, we are getting here the desired value around 1700 RPMs. We can add another pane maybe to see what is happening. We can see the output of the compensator maybe after the limiter. So what is happening here is that the difference is so great that we are applying the maximum duty cycle. Then we have here some nonlinear behavior, and then we are entering here in linear mode, so our compensator is generating the required signal to achieve the desired speed and the output. So maybe we can see other waveforms if we want. We can another pane and maybe take a look at the current through phase A and see how we are modulating and the current. So in principle we can see that everything is working well. And now what we are going to do is to add some step responses in the simulation. So we are going to check what is happening when we do a step on the load torque and also a step on the DC voltage applied to our system. Now we are going to see what happens when we apply a voltage step at the input, first in open loop and then in closed loop. So here we have this voltage source that we are going to apply at the time instant of 20 milliseconds and with an amplitude of 4 volts. So the step is going to be from 10 volts to 14 volts. And then here we are applying a value of 0.5, so the duty cycle that we are going to apply is 0.5 also. So now we are going to run the simulation and see the results. We are saving the information of the input voltage and also the angular speed, so we can take a look at the angular speed here. And then we will add another pane and show the DC voltage. So we can see how we have here the step up transient. And then we can measure things. For example, here we have that the speed is 1800 approximately RPMs, and then after the step up transient we have 2650 RPMs approximately. So we have this change because we are operating in open loop. Now we are going to simulate the same response with the step up transient at the input, but operating, as we can see, in closed loop. And then we are selecting here a value for the reference voltage of 1.7, so this is 1700 RPM. So let's see how it works. We are going to show the angular speed, and also in another pane we are going to see the DC input voltage. So we can see how after the initial transient we get here the desired value of the angular speed, and then we have here the step up transient at the input of the DC voltage, and we see how the angular speed keeps almost constant. So we have almost the same value before and after the transient at the input. So in principle our compensator is well designed. Now let's try another example. In this case we are going to perform a step up transient on the load, so we are adding here this other voltage, so that at time instant of 20 milliseconds we are adding 0.1 to the original load. Now we are operating at open loop, So we are fixing the duty cycle to the value of 0.5. So now let's run the simulation, see what happens in open loop. We are going to see, as usual, the angular speed on this pane, and then we are going to add another pane and take a look at the torque load. So we can see that at this instant we are increasing, doubling the load torque, and therefore, because we are increasing the load torque, and the angular speed is decreasing. So before the step up transient, we have angular speed of about 1,800 RPMs. And then after the transient, we have around 1,300 RPMs. So let's do now a simulation in closed loop to see how we can regulate the angular speed against this change in the load torque. Here we have now the same circuit, but now measuring the angular speed and sending it to the compensator, the limiter, and then the PWM section. So we are operating in closed loop, and we are adding the same step up transient at the input corresponding to the load torque. So let's see what happens now. We are going to see, as usual, the angular speed, and then in another pane we will show the input corresponding to the load torque. So we can see here how the step up transient occurs, and the speed, the angular speed, remains almost constant before and after the transient. So we have a speed which is around 1,700 RPMs as desired. We can also take a look in another pane, if we like, at the current through one of the phases, phase A for example. So we can see how the current in this part with a lower value of the load torque is smaller, and here the current increases because we need more power in order to keep the same angular speed with a higher value of the load torque. Okay, this is all today in this video. I hope it is useful for you. Please let me know, as usual, if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.